Okay, so the purpose of this video is to demonstrate the performance of the synthetic tracking technique as compared with what I call the conventional technique. So I put together a table here to compare the two side by side. So this is a program that implements the synthetic tracking technique, and this is results from another program that implements the conventional technique. So as you can see, synthetic tracking has very favorable performance. In fact, it has a 100% detection on magnitude 20, whereas conventional technique drops off rapidly and reaches 0 at just magnitude 19.7. Now, for those of you who may not be familiar, magnitude scale is not linear. So magnitude 21, for example, is 3 times fainter than magnitude 19.7. So you might see that these are, just small differences from one to the next, but they're actually large differences. Okay, so some of you might wonder, well, how did I come up with these numbers? So I used a tool called Astrometrica, which is a software program that implements, again, what I call the conventional technique. You feed it a series of 3 to 4 images, having regular interval from one frame to the next, and it attempts to detect objects that have consistent motion from one frame to the next. So what I've done here is I have injected a series of test targets into a given field of view. In fact, so there are 50 images, but again, I can only supply 4 images to Astrometrica. And so these images in particular have an amplitude of 400, which when you convert it to instrument magnitude, that corresponds to magnitude 18.2 for this particular setup. So we should expect to see 62% detection of these test targets for the amplitude 400. So I went ahead and selected 4 frames 5, 7, 9, and 11. So I feed these into the program, and I go ahead and run the moving object detection routine. So it goes ahead and performs some analysis. However, it wants me to do, it wants me to help it with this reference star alignment. So I click OK, and unfortunately you can't see all the test targets, so I have to rerun the routine again with this window moved where I want it. Okay, so do this one more time, and now you should see, and you do see these test targets. So it has 63 objects, and in fact one of them is in fact a real asteroid. So 63 minus 1, that's the 62 that you see in this table. So 62% detection of the amplitude 400 targets. So how about and that was again magnitude 18.2. So how about magnitude 18.9? Okay, so that's going to correspond to amplitude 200. So I have another folder for that, and we'll do the same process again. Let's see if I can move the window into position this time. Okay. Alright, so as you see, 38 objects detected. Again, one of them is a real asteroid, and the others are the test targets. So that's 37% detection of the amplitude 200 targets. So now, how does that compare with the synthetic tracking? So I go ahead and launch my program called Tycho here, and I run first off with the amplitude 400. Actually, why not just go ahead and start with amplitude 200 here, which is the mag 18.9. So that should also be at 100%. So I'll just save time and start with that. So run the tracker. Again, I have a user manual on how to operate all this, so I'm not going to go into all of the details at this point. So now it is running the synthetic tracker, and I am running this on an NVIDIA NVIDIA GTX 970. It's a 4-year-old video card, so it's not like I have a supercomputer or anything of that sort. And in fact, I'm also running this screen recording software at the same time. So, in my opinion, this is actually not too terribly slow for what it's actually doing. It's going through 50 images, and it's processing about 8,000 different motion vectors to detect any objects that have those particular motion vectors. And just by the way, that's also how I came up with the receiver operating characteristic curve. Is I use these test targets to determine the probability of detection for given threshold, and the different false alarm rates for each as well. So if you're curious how I did that, I use this test target injection routine. So, okay, the software is now finished, and it presents me with a track navigator window. And so the very first detection is that of the real asteroid. And so you can see that if I go ahead and bring up position window, I can have it move through like that, or if I wanted to, I can track the motion like this. So some of you may be familiar with that technique. Let me recenter it. So anyhow, but the point is that we do have 100% detection of these objects. So it actually came up with 117 tracks. So a few of these are actually, and it sorts them by quality. So a few of these are actually, they are significantly less quality. These would be, it managed to find, if you will, some noise that constituted what it thought was a detection. So it's a false detection. So again, you can mitigate that by setting a higher threshold if you want to. That all is, there's a science to that in and of itself. But needless to say, you can easily go through this list of targets here, and you can see that it identifies all of the detections that you would be interested in, and you can very quickly see them as true detections through visualization. Okay, so that's 100% detection, whereas the conventional technique only had 37%. How about this one here? So this would be amplitude 100. So again, we've covered 400, 200, and now we're on amplitude 100. So I can load that into the software. So I go up directory into the amplitude 100, and I can run the tracker again. Okay, so it has finished, took 70 seconds, and again we are presented with a navigation window. And so, again, the first object here is that of the real target, very high quality, and these have lower quality mainly because they are much fainter, and that, which is one component in the quality computation, is how bright the object is. To some degree, it's a component among others. So anyhow, yeah. So we have again 100% detection now of this mag 19.7, whereas the other had 0. And so if I wanted to, I could also show you what they look like. And that's the real asteroid. So here they are. I have the brightness turned all the way up. This is a median filter, so they show up very nicely in a median combine. But what do they look like on the image viewer? So turns out they're indeed quite faint. So you might wonder, is this really pointing at an asteroid? Well, it is in fact. Again, if I go to position window, I can do this. So perhaps you can see it there. If not, I can zoom in a bit more, and I can get rid of the crosshairs. So maybe you see the asteroids there. So again, they're particularly faint. However, it has no problem identifying all of them, and this is a very crowded star field, so it does very well. And you can see it has no problem detecting them. I can pick on any of these tracks here and look at its detection, and indeed it identified it in this very, very crowded star field. So I am a firm believer that the synthetic tracking is the way to go, and these results are, to me at least, they are quite impressive. So that wraps it up for this video. Thanks.